Hey, it's Neil Smith here. Hope you're doing well. The following problem seems a bit overwhelming, but be patient with yourself. It's just adding, subtracting, looking some numbers up in tables, throw in a few nuances, a couple concepts to keep straight, and before you know it, you'll be doing these problems. They're not that bad. You got this. All right, determination of compass error by azimuth of the sun, practice problem 2. And on 26 February, your vessel's 1615 zone time, DR position is this. Let's get all these givens. So we're problem 2, and we're going to get all of our givens. So we were given the date. Let's get the date. It's equal to 26 February. Feb 26th, all of these are 1981. And now our zone time is 1615. So our zone time is equal to 1615. Our DR position is given. DR position is equal to 2514 south, 25 degrees, 14 minutes south. That's our lat. Here, let me back up and put lat here because it's helpful to label all this stuff. There's a lot to keep straight. Latitude is 2514, 25 degrees, 14 minutes south. Longitude is equal to 57 degrees, 22 minutes west. And now the azimuth of the sun is observed. And here's the azimuth of the sun. Sun is bearing 266. So sun bearing equal to 266 degrees PSC. You can see it says per standard magnetic compass, PSC. Okay, here's the cron time. Cron time of the site is 8 hours, 13:19. Cron time is 8 hours, 13 minutes, and 19 seconds. And then it'll give the cron error is equal to cron error is 1 minute 46 slow. 1 minute 46 seconds slow. When it's slow, we add it. And the variation is 6 east, 6 degrees east. And it asks, what is the deviation? So we need to find deviation is what? Now, the first thing we can do is find the GMT, the approximate GMT, using our zone time and latitude. GMT. We'll just make sure we're in the right ballpark. So our zone time is equal to 1615. And then our longitude is 5722 west. 57 degrees west. This 22 minutes here, it shouldn't come into play. If things get kind of close, we can use it. But 57 divided by 15 equals 57 divided by 15 equals 3.8. That rounds up to 4. And again, that 22 minutes, if we turn this into a decimal, it would just push it further towards 4. So it's 4 hours. And we need to figure out, do we add or subtract this 4 hours? Well, if we look at a little graph here, if this is the prime meridian or Greenwich Mean Time, and these are the time zones, if we go to the east, we add. If we go to the west, we subtract. You can think of like New York to California, you're subtracting, but we need to get back to the prime meridian. So we need to get back here. So we're going to add if it's west. So this is going to be plus 4 hours. So 1615 plus 4 hours is going to 2015. This is kind of the approximate GMT. We know we're in the right ballpark. We're making sure we're in the right day and everything. Let's get our actual GMT based on our cron time. So we're going to get actual GMT. And the cron time is 8 hours, 13 minutes, 19 seconds. So cron time is equal to 8 hours, 13 minutes, 19 seconds. The cron error equals 1 minute 46 seconds slow. So we add it. 1 minute 46 seconds slow. So we add it. Let's add all this up. 19 and 46. 65. You notice there's 60 seconds in a minute, so we're going to end up throwing one over here, but let's just keep going. 14 minutes, 8 hours. So this would, we account for these, this would be 8 hours, 15 minutes, and 5 seconds. And this is our GMT. So check this out though. There's ambiguity in this chronometer. See how we are at 2015? Like, okay, this is 12. So there's the other side. It's like an analog watch. You have to figure out if you're in day or night and the right day. So if we add 12 hours to this, add 12 hours to 8, we get 20, 15, 05 hours, minutes, seconds. Now, this here, this is the one that looks like our approximate. This is why we find our approximate, to make sure we're not 12 hours off. And this is in the same day, so that equals the GMT, and it's on the date of February 26th. Feb 26th. And this is 1981. All these problems are 1981. So here's our GMT. It's not that one, it's this one. So with our GMT, we can figure out the Greenwich hour angle of the sun. So we can say GHA of 20 hours is equal to, we'll figure it out, and then GHA of the increments, which is 15 minutes, 5 seconds. These are both equal to something, but when we get these, the declination numbers are going to be right next to it. We need those too. So we'll get the declination and we'll get our decorrection at the same time. So let's jump into the Nautical Almanac, and we're looking for GMT 2015-05, February 26. So we start February 26. It's in February, so it's going to be at the beginning, April, March, February 15, 16, 17, February 26. And so there's 2 pages, February's 24, 25, 26. You can see these are all the stars and everything. And here's the column we're looking at, the sun, right here. And the GMT, the day, we need the 26th. And then we're looking for the 26th, and our GMT was 20 hours. 20 hours. So here we are, the 26th, 20 hours. We're 1:16:47. Let's record that. 116.47. So we're at 116.47. And now the declination's right next to that one, so we can get that right now. And we're at 20. So you see this south 8 right here? It's just implied that it comes down. So south 831. South 831. And it's decreasing, which tells us something. So south 831. South 831. And now that decreasing, this D value is going to be subtracted because it's decreasing. The D value comes from here. There's the D value of the sun. D, 0.9. So mine is 0.9. And now we need to get numbers from these increments. 15, 52, and 5. Let's make sure that looks too much like 52. These are seconds. Cool. So 15 minutes, 5 seconds. So we flip into the increments. 48, yep. 15 minutes. So here's the sun column, and here's 15 minutes, and then 5 seconds. 15, 5. So 3 degrees, 46.3. 3 degrees, 46.3. 3 degrees, 46.3. Let's make sure. 346.3. That is what we have. And now we can look at our D correction. Here's the D correction. Ours was 0.9. So we get to 0.9, and it shows that the correction is 0.2. And we're subtracting it. Minus 0.2. So now we can crunch these numbers up. Let's do the declination first. So 31 minus 0.2. 31 minus 0.2 equals 30.8. 30.8. South 8. 30.8. And now here we are for GHA, the sun. 47 plus 46.3. 47 plus 46.3 equals 93.3. 93.3. And this is 119. 116 plus 3 is 119. Now, look at all these minutes. If we subtract 60 and add it here, we get 120. It goes up 1 degree, and then this would be 33.3. Good. So this is the GHA of the sun. GHA of the sun equals this. And so now we need to subtract the longitude because it's west. It's west, so we subtract it. So minus west longitude, which equals 5722. 5722.0. This will give us our LHA. 33.3 minus 22. 33.3 minus 22 equals 11.3 minutes. And then 120 minus 57. 120 minus 57 equals 63. 63 degrees, 11.3 minutes. This is the LHA, or local hour angle, of the sun. Good. Now we have everything we need to start making this table. So in our table, we have to do this triple interpolation. And we start with declination, and we need dr lat, and we need LHA, the sun. Let's see what these equal. Declination is here, south 8, south 8, 30.8, 30.8 degrees minutes. And dr lat, 2514 south, 25 degrees 14 minutes south. Right now, you see this dr lat is south, and this is south. So right, we need to know that the dec and dr lat are the same. That's important that they're the same. Okay, LHA of the sun, we calculated 63 degrees 11.3, 63 degrees 11.3 minutes. Good. And now we can get into some tables. So we need to get our base argument. The base argument is just simply the degrees. So declination is 8 degrees, dr lat is 25 degrees, and the LHA is 63 degrees. Those are our base arguments. And now we need to get our base. With those, we can get a base angle, or Z, and we get these from the site reduction tables using these values and that they're the same. So we'll jump into these site reduction tables. We're looking for LHA of 63 and the same, and 25. So if we start flipping in here, we're going down 65, 63. So 63, the same, and 25. Okay, cool. Let's look at this. So what are we getting for our base angle? So again, 63, same, 25, and now a declination of 8. Here we are, 63, same, 25. So we're at 94.1. That's our base angle, 94.1. 94.1. We use it through all three of these. Okay. And now we need to get our tabulated angle, or tab Z. And this is interesting. You just bump this one up by 1 degree and leave these two. And then the second one, you bump this up by 1 degree, leave these two. And the third one, you bump this up by 1 degree and leave these two. And that's what this tab Z is right here. So let's, first, it's easiest to bump our declination up by 1, right? So we're 63, same, 25, and we, instead of 8, we look up 9. So here we are, 9 declination over to 25, Z, 93.1. 93.1. The second tabulation, we just bump this up by 1. So we go up by 1 here, 26. So we're at 63, same, 26. 8 is our declination. And 94.7 is what we're getting here. 94.7. And this last one is the trickiest one because you have to bump this up. You have to bump your LHA up by 1. So that means we need to turn the page. So this needs to be 64. Oops, wrong way. So again, they're the same, 64, 25, 8. There we are. So we're 64, same, 25, 8, 93.7. 93.7. Good. Now we need to figure out the difference between these two. So now we figure out the difference in the angle between the base and the tabulated. So what we can do, I always like to get if it's positive or minus. So if tab Z is less than the base, it's going to be minus. This one's plus because it's more. And this one is a little bit less, so it's minus. Just like to get those straight. So now you go, here you go, 93.1, 93.1 minus 94.1, 94.1 equals negative 1. I guess I could have seen that. Okay. So 94.7, 94.7 minus 94.1 equals 0.6. And then do the last one, 93.7 minus 94.1 equals negative 0.4. Okay, good. And now we record our increments. And increments are just these, the minutes. So 30.8 and 14 and then 11.3. These are the increments. Now we need to figure out the correction. And the correction is found by the difference times the increments divided by 60. So diff times increments divided by 60 will give you the correction. So let's work those numbers. So we go negative 1 times 30.8 equals divided by 60 equals negative 0.51. Negative 0.51. Now we'll do the next one. 0.6 times 14 equals divided by 60 equals 0.14. And now the last one. Negative 0.4 times 11.3 equals divided by 60 equals negative 0.08. 0.08. Now we add these together and get the total correction. We can start with a negative 0.51 plus 0.14 equals minus 0.08 equals minus 0.45. We're going to round this to minus 0.5 degrees. That's the total correction. So now we can use that. I like to line it back up over here. Our base Z is equal to 94.1, and our correction is minus 0.5, which gives us our Z value, which is equal to 94.1 minus 0.5 equals 93.6. Here's the tricky part. We need to name this. So we name it same as latitude. south. And then in this case, our LHA is less than 180, so we name it west. And now we need to figure out our angle from north, or ZN. And there's some formulas in the site reduction tables, but I just like to lay it out on a little graph, and then you can just kind of tell through common sense. This is north, south, east, and west. We're south, right? We name south and west, and we're up here because we're 93.6, so we're over here somewhere. So from south over here, this is Z. We need to figure out from north all the way. So this is ZN. So it's going to be 180 plus Z. So we can say ZN equals 180 plus Z, which is equal to 180 plus 93.6, 93.6 equals 273.6, 273.6 degrees. And now we can put it in our TVMDC and correct this compass. When we're going down, we add west. And true, we just calculated true, 273.6 degrees. Variation was given 6 east, 6.0 east. And when we're going down, we add west, we subtract east. So 273.6, 273.6 minus 6 equals 267.6. 267.6. We were given the compass over here, the sun bearing 266 PSC, 266 degrees PSC. And so we can tell we're going from 67.6 down. So this is going to be east because we need to subtract to get here. So 267.6 minus 266 equals 1.6. This is our answer that we're looking for, 1.6 east. Let's check it out. Number 2, looks like correct answer is 1.7. That is by far the closest. So we're saying number 2 is A. That's what we got. So that's the answer to compass, determination of compass error by azimuth of the sun, practice problem 2.